Okay, so we'll start. We'll begin a new method for statically indeterminate structure, but it's called virtual world. But to understand what is virtual world, so we will start first explaining what is the method of virtual world in a determinate structure. Like the deflection. When we started the deflection, we learned how to calculate some displacements, like horizontal displacement, vertical displacement, rotation at some point. And then we use this method when we begin the superposition method and the three-moment equation method. So in order to understand how to use something called the virtual world, we have first to understand what is virtual world in statically determined structure. So first, this lecture and I think another three lectures, we will learn how to deal with virtual world in statically determined structure. Like structure 1, determinate structure. Only we will learn how to calculate some displacement. What's the difference between this method and the deflection? Deflection, we also learn how to calculate some displacement. Deflection was a method called the conjugate beam method, right? We use it only with beams. When it comes with frames and we need to calculate some displacements, we use a method called virtual work instead of conjugate beam. Okay? So this method, the virtual work method, is the same criteria like the conjugate beam method for deflection, but for frames. We will learn how to calculate displacement not only in frames but also in trusses using the same method that's called virtual work. Okay? So this is a determinate structure, a statically determinate structure. So the requirement will not be draw bending moment and shear force, because it will be like structure 1. So the required here, please calculate some displacement. The first displacement called HB, horizontal displacement at B. The second displacement phi A, rotation at A. The third displacement, vertical displacement at point C, YC. Okay? So first, what was the first step when dealing with deflection? When dealing with deflection, the first step was draw bending moment diagram, right? This was the first step. Please draw bending moment diagram. So this will be the same step here. First step, it's a statically determined structure, so you can easily draw bending moment diagram, and we will name it M node. So let's remember how to draw bending moment diagram for a frame. This is structure 1, and I will send you the link for structure 1 videos how to draw bending moment diagram for frames. Mainly it will be only simple frames and arch frames. In structure 1, I think you studied the 3-hinged frame, compound frame, simple frame, arch frame, right? We will use here only simple frame and arch frame. So I send you the links to remind you how we draw bending moment diagrams for a simple frame and arch frame. Okay, so the first step, let's draw bending moment diagram. So we have to first calculate the reactions. Where are the reactions here? I have hinged support, so it has YA and XA. A roller support that has only a vertical reaction YB. Okay, let's remember how to draw bending moment diagrams for frames. The first step, you have to draw for each member individually. How many members do you have here in this frame? We have 4 members. AD, BE, DE, and DF. Any member that is intersected with another member, so this member splits the first member into 2 members, okay? So FE is not one member. FE was split at point D because there is another member, DA. So FD is a member and DE is another member. So here in this frame, this simple frame, I have 4 members. Okay, let's first calculate the reactions, but I have, in order to calculate the reactions, I have to concentrate the distributed moment. So now, after I told you that FD is a member and DE is another member, so how will I deal with the uniform distributed load? I will deal with each member individually. So DE 2 times 9, 18, and for DF 2 times 2, 4. So I have to split the distributed load when concentrating it because I now have 2 different members. Okay? I think sigma x equals 0 will be the first equation. I have 3 tons here at point E to the left. So XA has to be also 3 tons to the right. I don't have to write this equation. Okay? Now I have to write the equation of sigma moment to calculate the reaction. So sigma MA or B, as you like, equals 0, and I have to assume positive direction. Sigma MA equals 0, so XAYA will not have any moment. The first force that will have moment around point A will be 4. 4 times, what is the perpendicular distance between the 4 and point A? 4 is in the middle of the 2 meters, so 4 times 1. 4 times 1 is anti-clockwise, which is negative. So negative 4 times 1. And then 18 times, it's in the middle of the line, so 18 times 4.5. Clockwise, so plus. And then the 3, what is the perpendicular distance between the 3, the force 3, and the point A? The perpendicular distance will be 6 meters. So 3 times 6 anti-clockwise, so it's 9. So it's negative, sorry. Negative 3 times 6. The last force will be the YB itself. YB times 9. Also anti-clockwise, so minus YB times 9 equals 0. So YB from here will be equal to 5.56. 5.56 or 5? 6.56. Positive. Positive means that I assume the correct direction, so it's upwards. So YB is 6.56. Now I can use sigma y equals 0. I have 18 and 4, 22 downwards, and only 6.56 upwards. So YA has to be equal to 15, I think, 0.44 and upwards. So now I calculated the reaction. What will be the next step? Draw bending moment diagram that will be named M node. Okay? Okay, so let's remember again how to draw bending moment diagram for a frame. Again, I have 4 different members, so I have to draw for each member. let's start in calculating the moment and at points. In order to draw any bending moment diagram for any structure, first I have to calculate the moment at some points. Where do we calculate moments in the frame? Can anyone remember? What are the main points that I have to calculate the moment at in order to draw the bending moment diagram? The ends, the beginning and the end of the frame, that means A and B. And also F is a free end, so it is an end. So first I have to calculate the moment at A and at B and at F. I think the 3 points, the moment is 0. They are moment at the edge. So MA equals 0, MB equals 0, and F equals 0. Let's name the two new points here, like this will be G, and this is already named C. This was already named C, and take care. One of the requirements is vertical displacement at C. Just remember this when we are drawing now, okay? What is the second place to calculate the moment, to draw the bending moment diagram? So the ends, and then any point that have a concentrated load, and then joints. The joints. What's the definition of the joint? A joint is a point that have two intersected members or more. So E is a joint that has two members, so we call it twice joint that have only two members, and D is also a joint that has three members: DF, DA, and DE. So now I have to calculate the moment at C first because it has a concentrated load, and also I have to calculate the moment at G because also it has a concentrated load, and then I will calculate the moment at joints E and D. Okay? MC, right or left will be easier. I think MC right will be easier. MC right, 6, the 3 will not have any moment. So only 6.56 times 4.5. Nadine. 6.4656 times 4.5.
29.5.
How much? 29. 52. 29.52. And the direction it's anti-clockwise, right? And I calculated from the right, so I have to put an arrow anti-clockwise from the right of the number, so it's like this. So the tail will be downward. MG, I think left is easier. 0. There are no forces left of G, so MG left equal 0. Now I have to calculate the moment at the joint. All of this, you already know it from structure 1, but I know that you don't remember it. So I am repeating it to just remind you how to draw a bending moment diagram for a frame. Again, I will send you a link for the video how to draw bending moment diagram for a frame. Now I want to calculate the moment at the joint. How do we calculate the moment at the joint? First of all, you have to put the moment of the joint here in the main example. Let's start with the easier joint. Which is the easier joint, E or D? E is easier because it only has 2 members, and D has 3 members. How to calculate the moment at E? It's like a regular point, right or left, okay? But from here, it's a joint. So you have to decide where will you calculate the moment at D from? From EB or from EDFA, which is easier? And at the end, both will have the same value. It's like ME right and ME left. It has to be the same, right? So I think ME from this direction of EB will be easier. Is there any forces at the part EB that gives a moment at E? There is only one force, which is YB 6.56, and it passes through E. Is there any other forces that give moment at E or around E? No. So the moment here is 0. So the moment at E from the other side, it has to be equal to 0. What about the moment at D? It has 3 members, so I have to calculate the moment at D. First from the part DF, and then from the part DA, and then from the part DB. For the joint that has only 2 members, I chose to calculate the moment from only one side, and the other side has to be equal. But for the joint D that has 3 members, one side is not enough. So I have to calculate the moment from 2 sides, and then the third side I can predict, I can give an estimation. How much will it be? Okay? What are the 2 easier sides? I think DF will be one of these easy sides, and also DA. But DEB, I can estimate it. Okay? What is the moment at D from DF? It's only 4 multiplied by the distance 1. So it's 4, and it's anti-clockwise. Look how I put the moment on the joint. It will be like this. So I put the moment on the member that I calculate the moment from. I calculated the moment from the member DF, so I have to put the moment on the member DF. And it's rotating around the joint. Okay? What about the moment at D, but from the part DA? The YA will not have any moment. Only the 3 multiplied by 6, which is 18. Look at the direction. Look at the direction. It's like this. I put it on the member DA on the direction of 3 times 6. So now easily I can calculate the moment from the third side. Any point, the moment or sigma moment has to be equal to 0. Right? So what will be the moment at D? 4 and 18 is 22. They are in the same direction. So in order for the sigma moment at D to be equal to 0, so the third direction moment, it has to be 22 in the opposite direction. Right? So no need to calculate the moment from D at D from the long side, right? No need to do this. I can know the moment, which is 22, from the equilibrium of the joint, that sigma moment has to be equal to 0. Okay? Now I can do the bending moment. Now I can draw the bending moment, and again I said I have to draw the moment for each member. Each member does not mean that I have to get each member individually and draw the bending moment diagram. No, I don't mean this. I mean when you draw the bending moment diagram for the whole frame, just locate the moment of each member, let's say DE. So locate the moment at D and at C and at E, and then draw the moment at this member, and then go to the other member and do the same steps, like we will do now. Let's start with the member AD, the column here of the frame, the member AD. The moment at A equals to 0. The moment at D for DA, is it 4 or 18 or 22? The moment at D for DA is 18, right? What about the tail of the 18? It's on the left hand side. In structure 1, I don't know how you got this. I used to tell my students, pretend that you are inside the frame. Pretend that you are inside the frame. So look at this, at these members like this. So the member DA, when you locate the moment 18, so you can easily know that it's upwards when you are looking from this side, right? So locate it upwards like this. And no any distributed load on the member, so you can easily draw a straight line like this. What about the sign? I know the bending moment upwards is negative, has a negative sign, and downwards is, or has a positive sign, right? Is this upwards or downwards? This will let you know. You are looking from here, you are inside, so this will be upwards, so it's negative. Okay? Let's go for another member, for any other member like FD, the small member, FD. This one. The moment at F is 0. The moment at G is 0. The moment at D is 4 and the tail is up. So 4 up like this. But here the member has a uniform distributed load. So let's join 0 with 0 dotted and 0 with the 4 dotted. And here the correction will be a second degree parabola. All of this is totally structure 1. Totally structure 1. Okay? You have to remember structure 1. Structure 1, it's a basic subject. You will use it in structure 2, in soil mechanics, in hydraulics, in steel, in concrete. It's a basic subject. You are not allowed to forget structure 1, okay? So here is a curve, a second degree parabola, and the sign is negative. Okay, let's go to the corresponding member DE, the horizontal member DE. The moment at D is 22 and the tail is upwards. Right? And the moment at E is 0. And the moment at C was 29 and a half. Are you sure for 29 and a half? Downwards. Let's make a D. Okay? Let's make a D. We are now in structure 2, not structure 1. Okay? So when you see a member that has a distributed load, like we did in the 3-moment equation, okay? It's only enough to calculate the moment at the beginning of the member and the end of the member, and then join the beginning and the end and draw the curve with PL square over A. So no need here to calculate the moment at C. I just calculated it to remind you of some of structure 1. But here we are in structure 2, No need to calculate the moment at C, and no need to calculate the moment at G. So for the member DF, 4 and 0, and join, and then PL square over 8. For the member DE, 22 and 0, and join, and draw the curve with PL square over 8. Okay? Let's make a D. As we used to do in the stream moment equation. Okay? And this part will be negative, and this part will be positive. Let's calculate the PL square over 8. So the P is the density of the uniform distributed load, which is 2. L is 9 square divided by 8. So 81 divided by 4, I think it's 20.25, right? 20.25. What about the PL square over 8 here? It's 2. 2 square over 8, which is 1. 8 over 8 is 1. Okay? What about the last member EB? No moment on EB. Why? The moment at B is 0. The moment at E is 0. So no moment here. So this will be my bending moment diagram, and I name it M node. Okay? What will be the next step? The next step, now look at the requirements. Now look at the requirements. The first requirement, please calculate the horizontal displacement at B. Please calculate the horizontal displacement at B. Please draw the frame again, one more time, but without any loads. Now we will put only a unit load in the same direction of the requirements. So now it's required to calculate the horizontal displacement at B. So let B have a work horizontally. What is the work? That you have to put a unit load horizontally at B. So at B, put a unit load of 1 ton. This is the method of the virtual work. Okay? Okay, so I put here 1 ton to let the point B do a work in the direction he told me. He told me, please calculate the horizontal displacement at B. The method is called virtual work. So I have to let the point B do a work. How can I make a point do a work? I have to push it in the direction he told me. So I pushed it using a load in the direction he told me, which is horizontally. Okay? What about the direction left or right? I don't know. This is an assumption. I don't know the point B. When it moves horizontally, you know that a roller support can move horizontally easy, right? Take care, because one time in an exam, I told them to calculate the horizontal displacement at A, and A was a hinged support. Is there any horizontal displacement at a hinged support? The horizontal displacement at the hinged support is not allowed because there is a horizontal reaction at the hinged support. You know that the reaction eliminates the displacement in its direction. So no vertical displacement at point B because there is a vertical reaction at point B. And no vertical or horizontal displacement at point A because there is a vertical and horizontal reaction at point A. I think you know this, right? What about the fixed support? It has a horizontal reaction, vertical reaction, and a moment. So no horizontal displacement, no vertical displacement, and no rotation at the fixed support. Okay? And then draw bending moment diagram again, but for only the unit load. Okay? Can you draw bending moment? I think it's easier than the moment with the whole loads, right? It's only with a concentrated load, so I think it will be much easier. Okay? Let's calculate the reactions. What about the reaction XA will be equal to 1 in the opposite direction? What about YA and YB? Let's take a moment at A. So YB times 9 minus 1 times the difference between 6 and 4.5, which is 1.5. So the reaction will be downwards, and it will be equal to 1.5 divided by 9. 1.5 divided by 9. 1.5. 0.16. So YA here will be 0.16, but upwards. No any other vertical forces. Okay. How to draw bending moment? I have also have to calculate the moment at the joints first. The first joint at E. What's the moment at E from the side ED? 0. No moment here. Oh, sorry. 1 times 4.5, which is 4.5, sorry. So the other side has to be equal to 4.5 in the opposite direction. Right? What about the moment at D? From DF, no moment, 0. From DA, it's 1 multiplied by 6, which will be 6 in this direction. So the third side has to be equal to 6 in the opposite direction. Can I draw now the bending moment, which is named M1? Yes. Please draw the moment in the same drawing, okay? That's why when I put the square of the value of the moment at the joint, I put it on the side of the head of the arrow, because I know that I will draw on the side of the tail, right? So for the column AD, the moment at A equals 0, the moment at D equals to 6. And it's a negative moment. For the DF, no moment at the cantilever DF. The moment at D is 0 and the moment at F is 0. For DE, the moment at D is 6. The moment at E is 4.5 upwards. No correction. So I have to join it as a straight line. And it's also a negative moment. Can anyone tell me, in any moment for any requirement, will I see any parabola? Will I see any curve? Yes or no?
No.
It's yes and no. If it's a regular frame like this, where will the parabola come from? In the requirements, it's only for the unit load, right? No distributed load. A curve comes from a uniform distributed load. So how come I'm telling you now, yes, you can see a curve in any of the requirements. Do anyone know how? Can you remember structure 1? Do you remember the arch frame? The arch frame, when we draw bending moment diagram for the arch, there are conditions that there are not any distributed loads and the moments will be curved. But it's the only case when I am dealing with an arch frame. Okay? I can remind you now, there is an equation for the curve, which is x times f. I will repeat it again when we go through the arch frame, okay? But for now, I will not see any curves in any of the requirements, okay? And now I drew the moment which is called now M1. One here and node here is not related like the superposition. No, one here means for the first requirement. And for the second requirement, I will draw a moment, I will name it M2. And for the third requirement, it will be called M3 and so on. So it's like not case node and case one, the same like superposition, no, it's totally different, okay? How can I calculate HB now? Oh, okay. 4.5 and 3. And negative. How can I calculate HB now? HB, and I don't want anyone to be shocked, okay? HB is the integration of M node times M1 divided by EI dl. So the requirements, you have to integrate the moment that you already drawn now, which is called M1, with the moment of the loads itself, which was called M node, and then you have to divide it by EI. How can I make, or how can I do this integration? We know the integration for some equations, right? But it's the first time to integrate like diagrams, okay? So I will let you know now how to make an integration for two diagrams, okay? Please concentrate. Let's come here on the side. The first thing you have to know, if you are integrating two diagrams and the structure is a frame, you have to integrate each member individually. For this frame, I have 4 different members, okay? So I will integrate each member with its corresponding one. Let's say the column 80. What was the bending moment diagram for this member in case node or in M node? It was a triangle, right? What was the bending moment diagram for the same member in M1? It was also a triangle. So now I will give you an equation to integrate not a triangle with a triangle. It will be an equation for the integration for any straight line with a straight line. I mean no curves. There is only one equation to integrate a straight line with a straight line. And the general form for any straight line moments, what will be the general form for any straight line moment? Here, the moment is 0, right? And on the other side, there is a value. But the general form for any moment will be like a trapezium. This value is A and the other value is B, and the length of the member is L. The moment can be triangle, can be a rectangle, the two values can be equal to each other, and can be a trapezium, the two values can have a different, or the member can have a different value. So the general form will be for a trapezium. So the first member has 2 different values, A and B with length L, and let's name the factor or the inertia factor x. So if this is 2i, so x will be equal to 2. If it's 3i, so x will be equal to 3. So x here is the inertia factor. And I am integrating this with another member that have a trapezium as well, with another two different values, c and d. What will be the integration? The integration will be equal to, you have to know this. It's 1 divided by I, this one. I put it outside. And now I will give you an equation for the integration of m0 and m1. It will be L divided by 3x. 3 is a constant. And then open another bracket. The first value multiplied by the first value in the other member. So A multiplied by C. And then the second value multiplied by the second value. So B multiplied by D. What about the sign? If the two values you are multiplying by are on the same side, so the sign will be positive. If they are on different sides, so the sign will be negative. I didn't say if they are on the negative side or the positive side, no. If both values are on the same side, so the sign will be positive. For this one, this is the datum and this is the datum. So A is upwards and C is upwards. So they are in the same direction, so the sign will be positive. And also B and D, both of them are upwards, so the sign will be positive. And then the first value multiplied by the second value. So A multiplied by D divided by 2. And also positive. And then the second value multiplied by the first value divided by 2. Close the bracket and then close the big bracket. Let's do this here in the example to understand the equation with numbers. But first, I didn't put the inertia factor for the frame. I think, yeah, this is I, and this is 2I, and this is 4I. Okay? Let's start with the member AD. In M node, it has a triangle, and M1 is also a triangle. So 1 divided EI outside, which is 5,000. Open the bracket. L, which is the member length, which is 6 meters. Divided by 3, multiplied by the inertia factor of the member, which is 2. And then the first value multiplied by the first value. So 18 multiplied by 6. Are they on the same direction? Yes, both of them are on the same direction. So 18 multiplied by 6, positive. The second value multiplied by the second value, so 0 multiplied by 0. Nothing. The first value multiplied by the second value divided by 2, 0. The second value multiplied by the first value divided by 2, 0. So I am done. Okay? What is this? This is for the member called AD. You are now going to a new member, right? When you are going to a new member, please put a positive sign. Let's do the column BE. The column BE have a moment here, a triangle moment, and here the moment is 0. So is there any integration, a value with a 0? No. So I have here 4 members, right? But only 2 members will have values when I'm doing the integration. Because the member DF has a moment here in M node, but it doesn't have a moment here in M1. So DF is out. The member EB does not have a moment here and have a moment here. So it's out. So I will only integrate 2 members. The first member is AD, the second member is DE. Okay? And I am done now with the first member, which is AD. What about the second member, DE? What is the moment here? It's like a triangle, and then I subtracted a parabola from the triangle. So here I have 2 shapes, a triangle and a parabola. What about the same member here? What is the moment? It's a trapezium, right? So how many integrations I have for only this member, DE? I have 2 integrations. The first integration will be the triangle with the trapezium, and then the second integration will be the parabola with the trapezium. So this member by itself has 2 integrations. Let's start with the triangle with trapezium. So I'm still on the linear. It's called a linear with a linear. A linear moment with a linear moment. Linear means no curves, okay? So the triangle here, it's a linear shape, and the trapezium here is a linear shape. Plus, open a new bracket for the new member. L. L of this member is 9 meters. So 9 divided by 3 multiplied by the inertia factor for this member is 4. And then the first value, which is 22, multiplied by the first value here, which is 6. So 22 multiplied by 6. What about the sign? 22 is upwards and 6 is upwards as well. So both of them are on the same side. So 22 times 6 will have a positive sign. The second value multiplied by the second value, so 0 multiplied by 4.5, so it's 0. The first value, 22, multiplied by the second value, 4.5, but divided by 2. So 22 multiplied by 4.5 divided by 2. What about the sign? The 22 and the 4.5 are on the same direction, so the sign will be positive. The last term here, the second value multiplied by the first value divided by 2, so 0 multiplied by 6 divided by 2, which is 0. So I'm done here. Not done with the member. I'm done with the first part of the member, which is the triangle with the trapezium. What about the second part of the member, the parabola with the trapezium? This will have another rule, a different rule. When you are integrating a parabola with a linear curve, let's name it A and B, and the PL squared over 8, okay, and the length is L, inertia factor is X, the value of the integration will be the area of the parabola. The area of the parabola. What's the area of the parabola? So area of parabola which is 2 over 3 base times the height, and the height of the parabola is the PL square over 8. So this is the area of parabola. Multiplied by YCG divided by the inertia factor. What is YCG? YCG is the corresponding value in the linear shape with the CG of the curve. The CG of any parabola will be in the middle. So YCG means the medium value in the linear shape. So this is A and this is B. So this YCG will be A plus B divided by 2. So this will be the equation. Let's do it in the example. So now I want to integrate the parabola with the trapezium. What about the sign here? I didn't state the sign. It will be only one sign because it's multiplying values, no addition or subtraction. So only one sign I have to put it here. What will be the sign depending on? Is the parabola downward or upward? Downward or upward, it doesn't mean downward and upward the data. Downward and upward means, is it subtracted or added? What is this? Is there a bending moment diagram which will be having this shape? All the curves are downwards, right? When will I see a curve that have an upward in the arch? It's the only case that I will see a bending moment diagram that have a curve which will be added curve, okay? So for now, this curve is downwards and this curve is downwards because it's subtracted, okay? What about YCG here? Is it upwards or downwards? YCG here, it's upwards, right? And the parabola, it's downwards because it's subtracted. So they are on the same direction or different direction. They are in different directions, so the sign here will be negative. Let's do it here, okay? The curve of the parabola is downwards because it's subtracted. What about YCG here? YCG is this value, right? Which is 6 plus 4.5 divided by 2. Is it upwards or downwards? It's upwards. And the parabola is downwards, so the sign here will be negative. Area of parabola is 2 over 3, base 9 meter, times height of the parabola, which is PL squared over 8, 20.25. This is the area of the parabola. Multiplied by YCG, which is 6 plus 4.5 divided by 2. All of this divided by the inertia factor of the member, which was 4. And now I will close the whole bracket. What was this? This was the integration of the parabola with the trapezium. What all of this equation called, this is for the member DE. And this was for the member AD. So here, HB will be equal to HB positive 0.85 centimeters. This value has to make sense. What does I mean it has to make sense? A support, when it's moving, can't move from here to there. A support is like a column in real life, right? So it only moves a very small displacement, like 1 centimeter is big. 1 centimeter is big. So this is 0.85, so it's less than a centimeter. Okay, that makes sense. But you can't, from the calculator, tell me that it's 0.8 meter. What? 0.8 meter? The column moves from here to there 80 centimeters, so it doesn't make sense. So this value will be around 1 centimeter, not more than 1 centimeter. Okay? What does positive mean? What does the sign, positive sign, mean? You have to let me know to take the full mark, not only the value of the horizontal displacement. You have to tell me what is the direction of the horizontal displacement. Will point B move to the left or will it move to the right? Positive here means, can you remember the 1 ton? You put it going to the left, right? And at this moment I told you it's an assumption. So positive means that point B will move to the left. Positive means right, it's to the left. So it will move 0.85 centimeters to the left. If we have a bending moment diagram for any member that has this shape from M1 and M naught was a parabola like this, and the length was 6 meters, let's say, and it was 2I. Okay? And the PL square over 8 was 20. How will I do this equation? Area of parabola multiplied by y to g, right? What will be the area of the parabola here? So the integration will be equal to area of parabola 2 over 3, base 6 meters, times height, which is the PL square over 8, which is 20, multiplied by YCG. What will be the value of YCG? What will be the value of YCG? When the trapezium value was on the same direction, so YCG was 6 plus 4.5 divided by 2, right? This is also a trapezium, by the way. This is also a trapezium. Please don't split it to 2 different triangles. This is a trapezium. But the first value is downwards instead of upwards. So this shape counted as a trapezium. So YCG, let's draw it to scale. So it will be like this, 12 here and 4 there, like this. So YCG will be this value, right? This is YCG. So instead of adding the 2 values and divided by 2, so I will subtract the 2 values and then dividing it by 2. So 12 minus 4 divided by 2. Divided by inertia factor, which is 2. What about the sign? What will be the sign? Positive or negative? It depends. YCG is downwards or upwards? In this case, YCG is upwards, easy. But this case, when you are having 2 values, one is upwards and the other one is downwards, so the YCG will be in the in the bigger number side. So the bigger number here is 12, right? So the YCG will be downward or upward. It will be downward like the bigger value. So here the YCG is downward and the parabola is already or is also downward, so the sign will be positive. But if this was like this, so YCG will be this value like this, right? So it will be upward. So the direction of YCG when you are having 2 different values, one upwards and one downwards, the direction of the YCG will be with the greater value. The greater value here is 12, so the YCG will be downwards. The greater value here is upwards, so YCG will be upwards. Okay?